All right, so my name is David Sankel. I'm a software developer, software architect at Stellar Science, and we're going to talk about functional design. So before we get into what that is, I just want a show of hands for those of you who've ever worked on a code base and you've had this hairy code that you're working with and you have this aha insight and you simplify your code by figuring out one particular function or one particular piece, and you take these huge swaths of code and they become tiny little pieces just composing this little piece that you've created. So how many of you guys have come across that scenario, right? Okay, almost everybody. And this is really the idea behind functional design, is we're going after these aha moments. We're trying to find these extremely small, composable, powerful pieces that we can put together to make our software components. And usually when you do this, a normal programmer who is not familiar with functional design, you just kind of discover these things in practice. But when you're doing functional design, you're actually trying to find them directly. Let's see here. So just to kind of put where this is in context of things, I love putting up these two circles. So we have one circle over here, which is the engineering circle. People who are engineers, they are trying to solve real-world problems, right? They have a problem to solve. Whereas in the mathematical, more theoretical circle, you find people that are just trying to do interesting things, trying to push the limits of knowledge. But these two branches kind of intersect in the middle. And for example, an example of this intersection here would be asymptotics, runtime. That's a real pure mathy type thing, big O notation and such. But it's extremely practical when you're trying to solve a problem. But there are other things that are out there in math and they just don't really have a use for it yet. So what I try to do is I'm trying to put more math into practical engineering, or engineering to subsume more math so that we can take advantage of some of these theoretical concepts. And we're going to really build up to functional design. So it's not going to be, I'm not going to give you the formula from the get-go. We'll kind of build an intuition as we get there. So here's a quiz. And just shout out the answer. Do you think that the following two C++ programs are the same? Okay, there was some no's, some yeses. Now look, these two things could be in completely separate files, right? There is a difference between them. Well, they're in two different squares here. But fundamentally, there's nothing in these programs. We can say that they're the same. If I write these out to disk and I use the diff program, it's going to say, hey, these two things are the same, right? Assuming that there's not spaces in one and not in the other or something along that line. But anyway, so we're trying to build this idea of sameness, so we'd agree that this is the same for the most part. What about these two programs? What do you think? Are these the same program? I heard a yes. Anybody think they're not the same program? It depends. And it does depend. It depends on what the meaning is of the sameness, right? And we're trying to build an intuition here. So these things are not, if you use the diff program, they're going to say these are not the same, right? There's extra spaces in one. But syntax-wise, if you build a syntax tree for these two things, they're identical. They're syntactically equivalent. So what about these two programs? Here we got a program written in Python. And for those of you who aren't familiar with Python, all three of you in here, when you print something, it automatically appends the new line. So are these two programs the same? What do you think? Okay, great. So we had somebody say that they have the same output, so they're the same. Okay, and that's good. So these guys, so we're building this idea. We can even talk about the equivalence of programs if they're written in different languages, and one criteria could be that they have the same output, but is that good enough for us? What about these two programs? There's no output. Are these two programs the same? Just shout it out real loud. Yes, they are the same. There is an idea of these being the same because, for every input, they're going to have the same output. Okay, so how can we formalize this? Because we can come up with a bunch of different situations. They have the same output, they have the same functions, but we would like to get an idea of what is the essence of a program, and how can we talk about programs being the same as each other? So here are some properties we'd like to have. We would like whatever our essence is to have strong equivalence properties. So we can say this is the same as this, or this is different than this. Because without this, we're not really talking about sameness. So we need strong equivalence properties. We want something that we can write down when we talk about the essence of a program. So if I'm talking to a programmer and they say, well, in my head they're the same, and I say in my head they're different, if we don't have a way to resolve our difficulties, then we're kind of stuck. So we'd like to have something we can communicate with each other about the essence of a program. And finally, we would like to be able to take any program, apply a set of rules, and reach the essence of what the program is. So just go ahead and think about what kind of language we could use to get the essence of a program. Anybody have an idea?
Functions. So for f of x, any given input of x will have a discrete output, f of x that does not change if a function is the same as f of x.
So the comment is that we can use functions. And yeah, and that's only going to get us a subset of the way. But like going even more basic.
Mathematics?
Mathematics, exactly. So here we have strong equivalence properties. In mathematics, you learn in grade school, 3 plus 2 is equal to 5. Right? They're the same thing. It's just another way of writing 5. And 5 equals 3 plus 2. So this idea is a very old idea, is to take mathematics and map your syntax to mathematics. And this is from Dana Scott and Christopher Strachey. And here's an example of how they do this. You have this function mu, which mu stands for meaning. So the meaning of this syntax, and when you see the double brackets, we're talking about syntax, is equal to, now on the right-hand side, we're talking math, the meaning of this expression plus the meaning of that expression. So the plus on the left is a syntax plus. The plus on the right is a pure math plus. And then the meaning of I, where I is some integer like 1, 0 in syntax, the meaning of that is 10 in mathematics. So we can start building these strong mathematics. But then, we have a function. What are we going to say is the meaning of a function in mathematics? How are we going to have a strong equivalence for something like this? Well, that's actually not really a problem because we can have infinite sets. We can say a function is just a set of pairs mapping the input value to the output value. So if we have two different functions, we can talk about their sameness by looking at the set of values. And you can represent this in a few different ways. There's the lambda notation, and for those of you who are unfamiliar with lambdas, that lambda C, that's kind of like a C++ anonymous function with C as the input type, and mapping that to C plus 5. Or something else like f of C equals C plus 5. That's something you'd see in grade school, that kind of notation. But we do have a way to talk about the equivalence of functions mathematically. But what about this? How are we going to map this into math? Well, it turns out there's a problem. There isn't a straightforward way to map this into math. So this is the kind of problems that they ran into when they were trying to make a mapping from programs to their essence in math. And what they said is, well, we're going to make a new symbol. We're going to call this bottom. And if it doesn't return, we're going to say it returns bottom. And just like when you work with math and they first started discovering, oh, what are we going to do about square root of -1? And then we get I. And then you can build a whole algebra out of that. Well, the same kind of thing with bottom here. And I'm not going to go through all the different examples of things that we need to add to base mathematics in order to be able to grab the essence out of a program. But just to give you an idea so that you can do this. You can extend your math to be able to represent the essence of a program. Now, here's another idea. So Landon in 1966 wrote this programming language. If you see what I mean is what it was called. And it was just a purely theoretical language. It was just for the context of the paper. Nobody implemented this. And here's an example from his paper. His big idea wasn't, let's try to extract the essence out of programs into math. He just liked math a lot, and he'd prefer to program in math than to program in a language like Fortran. So does anybody recognize this code? Does this look similar to any kind of modern language that you guys know about? Haskell, yes. So all of the modern functional programming languages derive from this idea. The essence of functional programming languages is to program in math, because math has a lot of neat properties. So you see this, and then ML got derived from this, and eventually Haskell, but all modern languages look like this because they're trying to copy math. So, great, we can program in math. Why are we here? Because if we can just go Haskell, then I can just stop talking now. So, here's one reason. let's say we're doing a quicksort on it, and if you've looked at Haskell at all on the internet, you'd see this really beautiful quicksort implementation. It just turns out to be 4 times slower with optimizations than the first implementation I could find in C++ without optimizations. This is a problem. Now, some people who are really good at Haskell, they'll be able to say, you can tweak that, you can make it on par with C++. And I'd agree, you probably can. But what it ends up looking like is your program starts to look more and more like an imperative programming language. And you're defeating the purpose of Haskell in the first place, right? If you want to program in math, program in math. If you want to program something efficiently, you're going to have to know a little bit about the machine that you're working on and program that way. So this graph is a graph of abstraction. So on the far left of the graph, you've got that guy over there in very low-level abstraction. So he represents assembly language. You can get some stuff done in assembly, right? That guy can, put a roof over his head and hunt and eat, but you're not going to expect anything extremely interesting about him. Then on the far right side, you've got, one of these amazing new programming languages, Agda. It's esoteric even among the Haskell users. It's just a crazy language. It's so intense and neat that nobody actually writes real programs in it. And then to the left of him, you've got Haskell, right? So very high levels of abstraction. And then who's that big guy? C++, right? That guy is able to span the low levels of abstraction all the way to the extremely high levels of abstraction. No other language that I know of does that. So we have on the low level, you can twiddle bits, you can do device drivers. On the high level, you got template metaprogramming, which makes extremely interesting generic programming. And then with concepts, we get even further. But basically, any kind of abstraction that you can do in Haskell without any special extensions, C++ can do too, although more verbose. That's what we pay for that functionality, that feature. And then finally, we have the idea of semantics discovery. So this is Connell Elliott, who you see on the screen here, and he's a modern proponent of this methodology. But basically, you have a problem, and you're trying to find out what the problem is mathematically. So Newton, he did this, right? He's trying to figure out gravity. How do we model gravity? What's this problem? And he had to come up with derivatives and integrals and calculus, all to figure out how to model gravity and the different kind of problems that he was solving. So the idea of Connell here is you try to figure out what the essence is of your problem mathematically and then derive an implementation. So for him, he would write his essence into like Haskell-based math and then try to derive a more efficient implementation in Haskell. So now we have some ingredients here. So the idea of math augmented with some extra constructs can represent the essence of code. We have the idea of writing programs in math. We have the idea of C++, how it straddles all these different levels of abstraction. And finally, we have the idea of trying to discover the essence of a problem using math and then deriving the implementation. And that leads us to what functional design is. So the first part of functional design is you want to discover the mathematical essence of a problem and write it out. The second part is you derive an efficient implementation in C++ with the same interface that you discovered in step 1. And if you nail it, it works really well. So we're going to look at some examples, but first we need to improve our mathematical vocabulary with some new things. So the first thing we're going to talk about is algebraic data types. How many of you guys are familiar with algebraic data types? Oh, okay, so maybe 10% of you. So I'll go kind of quick. Actually, maybe I shouldn't go so quick for the 90% of you. So here's the 0 type. So we're talking about a type. It has no values. Here's how you implement that in C++. Now, this is a more theoretical thing. This doesn't come up very often in practice, but it's good to know about. So you cannot make an instance of 0. So that type has 0 instances. So can you guess how many instances the 1 type has? 1. And here's how you implement the 1 type in C++. You just make any class or struct with no members. You can make an instance of this. How many different instances are there of this? 1, right? So that's the 1 type. Those are our base two things there. Now we have operations to put our different types together.
When you say how many different instances of that there's one, that doesn't mean you can't instantiate it more than once. It just means that those are the same. Is that what you're talking about?
So the comment was the fact that you can only have one instance of it doesn't mean that you can only instantiate it one time. And yeah, I think we all understand that, right? We're just saying there's one unique value of type 1.
And the key there is unique,
And the key there is unique. Okay. Yeah, when we're talking about sameness when it comes to that, that's what we mean. Like how many different integer values do you have? You know, you can make lots of different instances, but you're going to have a set range of ints you can make on a computer. All right, so now we have the idea of a product. So given a value, types A and B, the product of A and B is the types whose values have an A and a B. And if you didn't like that explanation, you'll really like the next one because it's simple. Just a pair, right? A pair has a value of type A and a value of type B. An instance of a pair has a value of type A and a value of type B. But that's not the only way you can represent the product type in C++. You know, you can use a stud tuple. It's essentially, in essence, the same thing. Or you can use a struct. Now here, we're naming them, but that doesn't make any difference to, to the essence of what it is. It's still an A and a B. And when you do your semantics like this and you drive your implementations, you're going to have lots of different options. And that's where the engineering part of this comes into play. So what about this? Would this be a correct implementation of A product B? What do you guys think? No, I hear no. Why not?
Because you have an A pointer and B pointer, and they're not the same thing as A and B. These are simple view because an A would have memory space.
Okay, so there's the. Got it. So the comment was that the difference is because these have different memory locations, right? One is pointing to a piece of memory where the other one isn't. But in semantics world, memory doesn't matter, right? That's an implementation detail. Okay, and then there was a comment that it is a product type, and I think it isn't, but for a different reason. Because it can be null, exactly. We're introducing an extra state, and you got to deal with that. So the way you can deal with that is you can just write a little comment next to it saying that it's an invariant of this struct, that these things are not ever null, and then it models it properly. But generally, that's how it is. The comment was a pointer to an A is not an A. Well, the thing is, semantically speaking, it is a unique pointer in particular, right? So it's only there, it's only identified by that construct. When we map it to a mathematical thing, the only problem is null, not the fact that it's a pointer. All right, so the sum type, this one isn't really supported in C++ very well. But basically, you have a discriminated union. A sum type, whereas a product type, you have a value of type A and a value of type B. With sums, you have either a value of type A or a value of type B. It's one or the other. And you can implement this using something like this. So we have a little tag here, and it tells us whether the union has an A or has a B. And you put this little invariant saying, it's A when has A equals true, otherwise B. So that's one way to implement that. And that's fine and dandy. It's kind of nasty. Or you can use boost variant. So a boost variant is going to have a value of type A or a value of type B and give you a nice interface. And how many of you guys are not using boost? Shame on you. Use boost. Just kidding. No, not really. All right, so, or we're working on having a standard variant, and I put hopefully that'll represent, because there's some discussion as to whether they want standard variant to also have an automatic empty state. And that's a very contentious topic right now. And I'm hoping that it won't have an empty state and it'll correctly model the sum type. Okay, and so that's our basic algebraic data types. And now we also have a function type. And this is pretty easy. A arrow B, that represents a function that has an input of type A and an output of type B. This kind of maps to our intuition, except for the little point here that these are pure functions. So remember when we looked at a function and we tried to map it to a set, a pair of different values. If your function does something strange like output or change a global variable, or the same input can have different outputs depending on the state of your program, it's not pure. It's not going to be able to map to that nice mathematical representation. So we have to be clear that when we're talking about A arrow B in the mathematical sense, that it has to be a pure function in the C++ sense. All right, so moving on. Now we want to talk a little bit about meaning. So here we have that syntax. We got introduced to it before. So we have mu of this syntax is equal to some mathematical expression. All right, the meaning of that syntax is equal to this mathematical expression. And then we have down here, when you have an expression in C++, there's really two things you can say about it, right? You can say what its type is, and you can say what its value is. So we have to distinguish when we write out our mathematical expression here. So we use this colon here to say we're talking about what the type of this C++ expression is. And we use the equal sign when we want to talk about its value. So in the case of int, this isn't a C++ expression, right? This is a type. So we use the equal sign to say that this is equal to z. So z is the mathematical representation of the integers. Okay, so we're saying the meaning of int is the integers. And then the type of the meaning of 3 is the integers, but the value of the meaning of 3 is 3 in the mathematical sense of 3. So looking at some examples here, we have boost optional of where e sub 1 is some kind of type expression. The meaning of the boost optional is the meaning of that type. So if it's int, it'll be the meaning of int, it'll be z, or the one type. So an optional is either going to be none. You know how many different values of none are there? There's just one, confusingly enough. So it can either be the none type or it can be a int. So that gives us the meaning in mathematical form boost optional. And you'll see that when you take these really useful things that are in the C++ language and you try to figure out their meaning, you end up with very simple things. And that's what we're trying to go for. Remember, getting that simple essence of something. And then if you look at a pair, the meaning of a pair is the meaning of the first type expression product, the meaning of the second type expression. This is just the reverse of saying that products are pairs. We're saying pairs are products. And double can be real numbers, or maybe you really want to say that the meaning of double can be the real numbers plus these three other states. And these three other states would be negative infinity, positive infinity, and not a number, right? Because those otherwise don't belong in the real numbers. All right, so let's do some denotational design.
I was just wondering if you have to express the limits of those types, like doubles have a certain amount of numbers that it can represent in the math.
Okay, so the question was, do you have to express the limits of the numbers in your types? So usually when you're doing design work, you can live with an approximation. You don't have to have like the extreme rigor, but sometimes you do, depending on what you're working on. Yeah. So let's do an exercise. What do you think is the mathematical essence of a movie?
A bunch of frames, a set of frames.
Okay, one comment was a set of frames. Does everybody agree with that? Anybody have a different idea? What's that? Moving at a particular speed was another comment. Very good. Duh! A function from time to frame, yeah. But what is a frame? A picture? A function from xy to a color can be a frame. That's a great one. But we can go even more abstract than that. We can say a movie is a function from r, the real's time, to some other type. It doesn't have to be a frame. We can make an int movie. Why would you want to do something like that? Well, we'll see. But we can come up with some basic operations here. So the meaning of always is, so this is the lambda notation for this. We're just saying that always A creates a movie that for all time is going to have that value A. So if you want everything to be blue all the time, it's going to be a very boring movie. You can say always blue. Boom, you got a movie of blue. We can take a snapshot of a movie, given a movie and a time. We can take the movie, the meaning of movie, which we know is a function, and apply the time to it. So in our mathematical world, we can say that taking the snapshot of a movie at a particular time gives you the value at that time level. We can say transform things. So this one's kind of fun. So transform takes in something which converts an A to a B, takes in a movie of type A and returns a movie of type B. That's kind of fun. So let's say you have a black and white movie and you want to give it a little purple hue or something like that, but now it's not a black and white movie anymore. Now it's a color movie. So you can transform one movie type to a different movie type. And time movie, this is interesting. So we talked about you can have an int movie. Well, here's a double movie that represents the time at every point. So this movie at time 4 is going to have value 4. All right, this is kind of strange. But let's try to take these semantics and now assume we have an implementation of these things. And how would we make a gray flux movie? So a gray flux movie, this is where it starts out as white, and then in 1 second it goes to black, and then white again, and then black. Just a gray flux movement. So we start out with our time movie, and then we call transform with our function, which transforms a value of one type to another type. So time in seconds is going to be the input to that. And then we use the std mod f to basically get the part after the decimal point for the time in seconds, and then return a gray image with that kind of grayness. And that's it. And we've made a fluctuating movie. So you can see that we're coming up with these tiny little pieces, but you put them together and you get an extremely powerful language for defining movies. And if we had defined it in frames and all this other kind of stuff, we wouldn't get this kind of power. So again, we're trying to get to the essence of the problem that we're trying to solve. Let's look at another example. What's a stream? I'm not talking about one in a river. Anybody have any idea what the essence of a stream could be?
So in that one, so for a movie, we took our real value times and mapped them to output. Maybe in the stream, we can take our, you just get whatever's the next one instead of inputting it on. Is that?
So I heard the idea of taking the next one. Yeah, so we're getting kind of a sense, maybe not extremely concrete. And I'm sure you guys would figure it out if we had more time to brainstorm this. But here's one way to do it. Start out with the idea of a sync. So a sync, we're introducing this term action. It just means it does some kind of computation or stateful thing in C++ world, and we can do that. We can extend our math with that. It takes in some value, like let's say it's a double sync, and it will produce some kind of action. It'll do something, okay? And then we have the idea of a source. Now what that does is a function that takes in a sync, basically, and does something. So the only thing you can really do is just call that sync over and over and over and over again. If you want to have a source that consists of 5 5s, then it would just call the sync 5 times with 5 as its argument.
In the notation, why wouldn't you use sync of E instead of the expanded form?
The comment was, in the notation, why not use sync of E as opposed to the expanded form? Well, you could use mu of sync of E, and that would be equivalent. So that's fine. So we could directly map these things into C++. There's no problem with that. This isn't the only way to do it, though. You could do it with concepts as opposed to using std function here, and that would work just the same, except be a lot more efficient, actually. So now we're going to implement some sources and some sinks. So we have our source, which is now our console input, and it takes in the sync. That's what sources do. And it's just going to use cin.get and call the sync with it until there's nothing left. Simple enough. And then our console output is a sync, And this just is a function which takes in a character and outputs it as a standard output. Of course, sources and sinks are not very interesting on their own. It'd be nice if we had some way to connect them together. So we can do that. We'll introduce this idea of connecting a source and a sink. So the connect function, the meaning of that, it'll be a function which takes in a source and it'll take in a sink and it will do something. So in this case, concretely, if the source is SO and the sink is SI, we take the meaning of source. Now remember that a source takes in a sink as an argument, and we pass in the sink. And that's it. So we can directly implement this in C++, and that's what it looks like. And now we can connect our console input and our console output, and it just connects them.
Is it correct to say that a source is a special kind of sink, since a sink takes something and returns an action, and a source takes a sink and returns an action?
The comment is the source a special kind of sink? Because they both do an action, and I'd have to think about that. So anyway, we have this connect function, and this works. What other kind of things can we do? Well, we have here for reference that a meaning of a sink is something that takes in a value and does an action. What about the idea of transforming? So a transform from A to B takes in a sink of B and converts it into a sink of A. And you'll see why I reversed A to B to B to A in a second here, which is the same thing as saying the meaning of a sink to a sink here. That's like one function. But we can just say this is a single function which takes in a sink and a value of A and just does some kind of action. We're just moving things around a little bit. So a transform here, we can say that it's just a function which takes in a sink of B and an A, and that's all a transform is. So transforms on their own aren't very interesting. We can apply it to a sink, and that's what it was intended for. And I'm not giving you the implementation. This is an exercise, and I encourage you guys to just do it. It won't take very long, but it'll be very rewarding. So we're just applying this transform to a sink, and it produces a new sink. But we can also take our transform and apply it to a source. That's not a problem. And it's actually really fun to try to figure out how to do this. So we can apply this transform to a source. Now we're introducing some extra syntax here, just because we like to do operator overloading in C++. And we're saying that if you have a source and a transform, this syntax, source, arrow, or source, right shift, transform, the meaning of that is the same thing as the meaning of applying that transform to that source. And taking the transform and right shift to the sink, that's just applying the transform to the sink. And if we have a source and a sink, and we're using the right shift operator, we're just connecting the source to the sink. So let's look at an example. Let's say we have this getLines transform, and these are also exercises for you guys. And what this does is it'll transform a source of char into a source of, that should be string. Sorry. It'll transform a source of char to a source of string, and it'll just basically take that char source and convert it into a bunch of strings representing the different lines that got read from whatever. Then we have unwords, and this will take a source of strings and convert it into a source of chars, and it'll just take each of those strings and then make that source output the string and then a space and then the next string and then a space and then the next string and so on. And now we can use some of our neat little syntax. We can say, okay, input lines. We just take the console input and we apply this getLines transform to it, and boom, we got the lines. Or we can have this word output sync. Now we're taking a transform and applying it to a sync, and then we get a string sync. And then we can take input lines and put that to word output, and it does what it needs to do. So another thing that would be interesting is we can take a transform and apply it to a transform as well. There's nothing stopping us from doing that in mathematics. Again, that's an exercise. So here we just make a new transformer out of these two transformers, where it just uses the getLines transformer and it binds it to the unwords transformer, and boom, you get a new transformer. So my hope is that you're getting the sense that we get these pieces that we can put together in all these different ways, and we get a very powerful domain-specific embedded language, essentially. So that's what happens when you start with the mathematics and you try to build your way down to the implementation. So I got one more example. What is command line processing? So I'm sure all of you guys have used some kind of a command line processing library, like whether it's getopt, boost program options, something or other. And I'm always very disappointed with them because I just ask the question, well, let's say I don't want to use double dash and I want to use single dash. Well, then you got to make a modification to the library and add new features to it. Well, let's say you want to only have these options enabled if this prior option is enabled. Well, then you might have to add a feature, and then your library just grows and grows and grows and grows. That's a good indicator that whoever wrote the library didn't nail the semantics in the first place. If you nail the semantics, you can take these strange cases and it can do it. It's perfectly capable of it. So command line processing, when you think about it, you're really just taking a list of strings and converting it into some kind of value that makes sense for that program. And then you're saying, oh, well, that looks kind of similar because I know that the semantics of a parser, like an A parser here, where A is like a char or something like that, it just converts a list of some type into another type. So maybe a command line processor is really just a parser of a list of strings. So a string parser, so instead of char here, like you'd normally have with a parser, now you have a string. And so an example of how you'd use something like this is, let's say you have your help flag and your user flag, and the user flag needs to specify the username or something like that. You can use what you already know about parsers and make a little parser combinator library that works for command line arguments. So here we have mix args here, so if you have dash dash help, it'll have the help flag object. If you use dash dash user followed by a string and then convert that string into the user flag, now you just have a simple parser fully capable of doing anything you can possibly imagine. Expanding upon this a little bit, let's say you have your list accounts mode. So Git is a good example of a command line program that has different modes. So only if you have a certain mode open, like Git submodule, will you get certain options available for you. We have our total command line parse. This is the result of all the command line parsing. First you have your global flags. We already had a previous parser which handled that. And then you have a variant, which is either the list accounts mode or the list job mode. And we take the parser we defined on the previous slide, and that should be followed by one of these two. So we use the or here to say either this argument or this argument. And it just works. Extremely powerful. There's not much you can't do with it. That's what we're going for. So some of the benefits of this design methodology. You get highly flexible systems. It's hard to find cases that you can't use whatever program you came up with. It's hard to find cases where you need to add a feature in order for it to actually work for a problem domain. And the pieces are highly composable because mathematics is highly composable. So you're going to come up with these little pieces that can be used in all these different ways to put together complex programs, but the underlying pieces are very small. All this stuff is really type safe if you do it well, and the underlying pieces are simple. When you put them together, you get more sophisticated things. So this concludes the talk, and I wanted to give some time for questions, but the idea is you're discovering the essence and you're deriving the implementation. And there's so much more to this, like the mathematics behind it are just things that are extremely interesting. So with that, we'll answer some questions.
Is there a sample of this code online anywhere?
So the question was, is there a sample of this code online? There isn't, and that's because I want you guys to implement this stuff. So
I'm still not convinced about the some type example with the unique pointer. isn't the type inside the structure relevant? Can't you just alias unique pointer array, unique pointer B to B? Isn't that a some type? I'm not getting why it's not a some type. Sorry, product type. Sorry.
Okay, so the comment was that why isn't that unique pointer example just, why isn't that a valid product type? And the reason is because of the null case. Because if I try to map a value which one has null and the other one has null, I can't figure out the mathematical equivalent of that in the product type. The map doesn't work both ways. So that's the problem. Other questions?
So I know you want us to work out stuff, but I still want to read more about this. So what are some good sources?
Okay, so the comment was, what are some good sources if you want to read more about this? There's a book that I really like. It's called Denotational Semantics. I believe it's written by Schmidt. It's an old book. You can find the source. You can find the PDF online. It's out of print. And if you can get a hold of an old copy, then...
So is this the standard denotational semantics that's been around for decades?
The question is this the standard denotational semantics that's been around for decades? And the answer is yes. Any other questions? One in the back. So the question was, how does C++ relate to value, or how does functional design relate to value semantics? And I think the answer to this is that it maps very, very well. I think it makes C++ very well suited, because it has value semantics, to doing this kind of design. Whereas if you only have reference semantics, it's a lot harder to get those mappings. Yeah. Can I point to programs or libraries that have using this kind of a design and I think are well done? Well, there's another talk on Boost Spirit that's going on exactly at this time. So I'd recommend you watch, no, I just can't do that. But there's quite a few things out there. So generally, like Boost Optional, it nails the semantics. But generally speaking, this is something new in the C++ world in particular. You'll see a lot of this in Haskell, but not so much in C++. And I can tout some of my own libraries like SFRP. If you look that one up on the internet, you'll find a good example of that.
So I work in the embedded world specifically, so a lot of what we do is actually a lot of I/O. You take something from one place, you put it in another place. You might play with it a little bit, but not too much. Is there any way you kind of, I saw your stream example. Are there any other tricks you would say for things where you can't just purely express them in math, where it's actually more of sort of like an engineering problem where you're just moving stuff?
So the comment was, what about an embedded world, when you just have to move things, for things that are more difficult to express in pure math? And that is functional design, right? So you have to take a look at your problem and see if you can find the mathematics behind it. There are some problems that might be too complex to be able to find the mathematical essence of it, or they're just too difficult. People are discovering these things all the time. So it really depends on the particular instance of the problem to see, can we find out a good mathematical essence for it?
Have you thought about some ways to further kind of massage the syntax so it really does look more like math, so that someone that's not a C++ expert could work in that environment?
So the comment was, have I played with syntax that's even more mathy so that someone who's not a C++ person can work on it? And I think the essence of the mathematical language is pure mathematics. The only time when C++ is getting introduced is on the left side of that meaning function over there. So, and I'm using a very simple mathematical language here. So most of what I do in practice, I use the language AGDA for defining as my mathematical language for semantics. Yeah. So the comment it was, for the mathematical language that was used, can we get slides or something? And I think that all the slides are published online for this conference. I could be wrong about that, but if not, I will make them available. Yeah. So the comment was, it seems like functional programming requires a garbage collector. And functional design doesn't require a garbage collector. There's a lot of functional programming that doesn't require a garbage collector. So that's more in the functional languages kind of area. And you can do reference counting, and there's lots of different ways you can handle that problem if you're trying to implement a functional language. But you don't need it when you're mapping stuff to C++.
Functional design fundamentally incompatible with object-oriented design.
I'm glad you asked that question. The question was, is functional design incompatible with object-oriented design? My answer to that is, it makes object-oriented design look very bad. So generally, if you can come up with a functional design, it'll be very hard to argue that an object-oriented approach would be better. But it's certainly not compatible. You can mix the libraries together, just because we're using plain C++ functions. So there's nothing inherently incompatible, but I think it does supersede things like design patterns and other design methodologies.
So at your company, like an example of you write an ACTA and then other people later implement this in C++, and this is a way of expressing yourself, or maybe you can give us an example of how you use it.
Okay, so the question was, is there an example of how I use this at my company where I work? So one example was, I looked at this one class. It was called calculation. And it was a terrible class. Boy, is this being recorded? But anyway, we were trying to figure out how to refactor it. So what I did is I tried to figure out what is the essence of this calculation class. And it had like ID and all this other kind of stuff. And we had the aha moment that, oh, this is really simple. This is just a function of some kind. And then we reworked everything, and we realized that we didn't need an ID because we're just doing function equality, which is fine in math. So we overloaded the equal operator, and everything just got a lot simpler. So doing the design process is something that requires someone with a little bit of mathematical knowledge and discipline can do. But the resulting library is something that anybody can use, highly consumable. Another question.
Just because you did mention ACTA, things like common interest ACTA, a lot of them come with not just obviously functional language, they come with like model checkers, things that actually check to make sure the math you wrote is sound, because they are implementations of math. Is there anything that you can say like might help you take something from that domain that's just pure math and then kind of translate that into something C++, but still as sound from the standpoint of saying your program is correct as in verifiably correct, not just it didn't crash?
So the comment was that in a lot of these higher level functional programming languages like AGDA, you have a way to type check soundness. Is there a way to have an automated proof that proves that your C++, which is derived from it, correctly models what you're trying to model? And there's nothing that I'm aware of yet for that. So all of the proofs would have to be manually as far as I know. But they're not hard proofs to do. All right, well, if there's no further questions, find me afterwards if you have a question, but that's the end of it.